All in all, grades went up. Not a huge amount, but a sufficient amount. The spread is different. But what's important to me is that you go back through this exam. Because if you'll notice, everything we've been doing in the new chapter requires us to be able to do all these derivatives. I need to have the derivative to figure out what's going on. And if the mistakes you made were in the first, 8 parts, where it was all like, take the derivative, take the derivative, take the derivative, we need to make those get fixed. Even if it was the logarithmic derivative or the implicit derivative, you need to know what happened in there. So if you have questions, I did post the keys. You have now your exam to compare it to. And yes, there were 2 different versions this time. So take a look, come talk to me if you've got questions, and we'll go from here. Meanwhile, I want to talk about limits some more. William Francois Antoine Marquis de l'Hôpital retired from the military due to extreme nearsightedness, forced out. Decided to pick up mathematics and was reading books on calculus. Actually, at the time, it was called The Study of Infinitesimal. Little bitty pieces. Wait a minute, that sounds like a dx. Okay, I see where we're coming from. And he is talking to one of the Bernoullis. There's a whole lot of them. And he says, I want you to tutor me. I want you to help me understand this. And together, L'Hôpital gets a bunch of notes from Bernoulli and turns it into a book in which he talks about the analysis of differentials, which is done strictly geometrically as opposed to algebraically. This paper is from the Teaching Undergraduate Mathematics with Primary Sources list, the Triumphs page, and is by Daniel Otero. So this will aid us. I'll post it to our Canvas page if you're interested in where this came from. I promise we didn't spring full forth from the head of Zeus like Athena. It had to be developed. But what does L'Hôpital's rule tell me? L'Hôpital's rule tells me how to deal with indeterminate forms. And that's a phrase I've used before. So I know you've heard it before. All the way back in chapter 2. In early September, we talked about indeterminate forms, where we did things like this. How did we compute this limit? I can factor that numerator. When I look at it, though, if I just go to plug in 2, the limit of the top is 0, and the limit of the bottom is also 0. So I have 0 over 0, and that was our indeterminate form. And I said I couldn't determine what it was, so I needed to do something else. And the something else in this case is to factor and then remember we said, hey, if we're looking at the limit as we go to 2, then I don't care what actually happens at 2, so I can cancel those out. And then this limit just becomes the limit as x approaches 2 of x plus 2. And that's continuous there. So I can just plug in. But L'Hopital actually was working with not polynomial functions, but other functions, like the logarithm. And he noticed this has the same problem. If I go to plug in, what's ln of 1? Oh, crap. Again, I'm stuck. And there's no factoring I can do. You can't factor a logarithm. There's nothing there to factor. So I can't play the same trick. But not only this, he said, hey, wait a minute, take a look at this function. Instead of going to 1, let's go off to infinity. Well, as x goes off to infinity, subtracting 1 from it does make a bit of difference. So that's going to go to infinity on the bottom. What happens to ln of x as x gets bigger and bigger and bigger? Draw the graph. Graph of ln of x, as x goes off to infinity, continues to go up. That also goes to infinity then. That's another indeterminate form. I can't divide infinity by infinity. That doesn't make any sense. But I have actually divided infinity by infinity. You did it on exam 1. You have your copy of exam 1 with you? If you do, go to the very last problem of the first page. We had a limit as x went off to infinity, right? Of one big ugly polynomial over another big ugly polynomial. We did limits going to infinity like this. What's that limit? We divide by the highest power of x in every place. So we get 1 plus 1 over x squared on top, and then 2 plus 5 over x squared on the bottom. As x gets really, really huge, these go to 0, and I get 1/2. Even though, as x goes to infinity, the top of that original fraction goes to infinity, and so does the bottom. This is indeterminate of infinity over infinity. but I can fix it. So there's hope. Because I see if there's a 0 over 0, maybe I can do some fudging and I can get a value. I can determine what was indeterminate. Same thing if I have infinity over infinity. So Bernoulli, in his work with L'Hopital, comes up with a result based on Rolle's theorem and the mean value theorem. And he says that if you're really looking at what happens and both of your values are going to 0, you could visualize that. Think of two functions whose limit is both 0 as we approach A. Now I'm going to make the assumption that f and g are both differentiable at A. So they have nice derivatives. And that means they have nice graphs because they must be continuous at A also. Well, if they're continuous at A and their limit is 0, they both go through that dot. So I'm going to draw two pictures. A graph that is f of x and a graph that is g of x. And if I zoom in close enough, since these functions are differentiable, if I zoom in close enough, what do I see instead of curves? Straight lines. Because as we get closer and closer and closer to a point where we have a derivative, you can't tell the function from its tangent line. So let's change the picture. And instead, we'll look at the same point A, but we'll look at a real close-up. I'll see two straight lines, won't I? But as far as I can tell, those are just close-ups of the curves, right? That's zoomed in really tight. But if those are straight lines, then they could just as well be the tangent lines, couldn't they? And if I'm dividing f by g in this picture, then I could divide f by g in this picture. But I could swap them out for their tangent lines, couldn't I? Which means instead of using the original functions, I can use the derivatives. Now, the proof of this is actually a complicated piece of algebra that we're not going to touch. It's gross and disgusting, requires us to look into the nitty-gritty in Rolle's theorem that we really didn't do. But what it means is that I can write the following theorem. And because L'Hopital was paying Bernoulli, he gets credit. L'Hopital's rule, if the limit as x approaches A of f of x over g of x is indeterminate of the form 0 over 0 or infinity over infinity, then the limit as x approaches A of f of x over g of x is equal to the limit as x approaches A f prime of x over g prime of x. In other words, factoring, rearranging, redefining all of the 1 over x squared or whatever else I need in there. I don't need to do it. I can suffice to take the derivative. Let's go back and look at the examples we were looking at earlier. Limit as x approaches 2, x squared minus 4 over x minus 2. That was of the form 0 over 0. Yes, ma'am. The form. Indeterminate of the form. That is a horrible looking T, isn't it? There we go. I said I'm sorry if I didn't write anything clearly. Of reform. Now, how do you reform a, wait a minute, no. I apologize for my handwriting. We know what that limit is. We did it already. But we did it by factoring. Well, I'm going to say, wait a minute. This is of the form 0 over 0 if I try to evaluate directly. So, by L'Hopital's rule, I can replace f by f's derivative. We are not doing the quotient rule. L'Hopital's doesn't do the quotient rule. It just does the derivative of the top separately from the derivative of the bottom. Marcia? Oh, yeah, it did. Thank you. No, it shouldn't. Bad ducks, bad ducks. Okay, derivative top. Derivative of the bottom. Be careful. And then I can just plug in because I know how to do that derivative. That limit works. And isn't that the same result we got? It's a whole crap ton easier than factoring, isn't it? There's a reason I didn't teach you this first. We didn't know what a derivative was until we could figure out how to do limits, right? I couldn't do it in the other order. Ladies and gentlemen, that's like giving a baby running shoes. It's really, really worthwhile, right? No, you can't do that. You don't know how to walk yet. But now that means I can do this one. The limit as x goes to 1 of ln of x over x minus 1 is indeterminate of the form 0 over 0. So by L'Hopital's rule, I can replace this derivative of the top, derivative of the bottom, which gives me 1. No factoring required, no crazy psychotic behavior, but I have to know how to do a derivative. Now, I'm a little more pedantic about this. Every time I use L'Hopital's rule, I try to write it down somewhere that I use L'Hopital's rule. I tend to write LH over the equal sign. Hey, I did L'Hopital's rule here. I didn't just change the functions for the hell of it. Now, what about our infinity over infinity? Again, I know what this limit should be. But I had to do the divide by the highest power trick, or use the coefficients of the highest power. And that requires me remembering something from a long time ago that I don't remember, but I know how to do derivatives. So I'm going to use L'Hopital's rule, and I'm going to do derivatives. Derivative of the top. Derivative of the bottom. And if I simplify that, the x's cancel, I get a half. That was also infinity over infinity. But now I can do that. Using L'Hopital's rule, I can say, oh, this is going to be the limit as x goes to infinity of 1 over x over 1. Wait a minute. What's that limit? I now know how to divide infinities. However, I really need to be careful. Something I have omitted to write down in all 4 of these examples is important. What do you do? I'm sorry? Yes, absolutely. As long as the limit is going to work out to 0 over 0 or infinity over infinity, I can take it from one side, from the other, any limit I want. So I do L'Hopital's rule, right? I didn't check. In any of those problems up there, I didn't check that it was actually 0 over 0 or infinity over infinity because we've done it before. I need to check. If you go to plug in, what is sine of pi? Trig time. Sine of pi is 0. Cosine of pi. So this actually works out to be 0 over 1 minus negative 1, which is 0 over 2, which is 0. I don't need L'Hopital's rule. You must check in advance of doing L'Hopital's rule that you actually can use it. Now, the AP curriculum says you have to take the limit of the top, show it's 0 or infinity. The limit of the bottom, show it's 0 or infinity separately from one another. Showing that the limit is 0 over 0 in one step is considered bad form. I don't give a flying rolling donut about that. But I need to see that you have shown somewhere that you do have an indeterminate form for us to be able to use this. Questions? It's not needed, that it cannot be. It can't be used. You don't satisfy the criteria to use the rule, you can't use it. You were able to determine it beforehand. Why would you need something about indeterminates? Let's try this one. Is this an indeterminate form? When I go off to infinity, what happens to e to the x? That goes up to infinity. X squared, infinity. It's of the form infinity over infinity. So I do L'Hopital's rule. That's exactly what we're comparing. We're comparing the rates at which they go to infinity. That's what our derivatives are, right? Rates. And that's what we're trying to determine. Which of these is going to win in the race to infinity? If you think about the one that we worked out that came out to a half, x squared plus 1 over 2x squared plus 5. They're both parabolas, right? They're going to infinity. And they're kind of neck and neck with each other all the way there. So the rate at which they go to infinity closes in. The ratio between them is a half. In this case, the ratio between the two things going to 0 and 0 is 1. The ratio of the two things, oh, here the bottom goes to infinity much faster than the top, so this works out to be 0. It is exactly that rate comparison that I'm after here. What happens when I do L'Hopital's rule? Aha, e to the x over 2x. Houston, we have a problem. That's still infinity over infinity, isn't it?
What's the final point to say that either the numerator or denominator increases significantly faster?
Let's take a look at what happens here. If it's still infinity over infinity, I can do L'Hopital again. It's still indeterminate of the correct form for me to do L'Hopital's rule. There's no reason I have to stop once. Do it again, do it again. And now I get the bottom is definitely not going to infinity anymore. It's no longer indeterminate, but what is the top doing? The top is still going to infinity. Half of infinity is still infinity, right? The top function here grows so much faster than the bottom that it outpaces it, that the gap between them grows to be huge. The rate is so much more for e to the x than it is for x squared, that this ratio is infinite. That's what it means to grow a lot faster than something else. $64,000 question. Why should I give a flying? How many of you used an internet search in the last week? How does it work? If I give you a list, let me do it a different one. If I give you the exams for the class and I say alphabetize them, but the last thing I did was play 52 pickup with them, they're in a random order, how long is it going to take you? Here's a deck of cards. It's in random order. Put it in order. Ace through king, spades, hearts, clubs, diamonds, in that order. Put it together. How long is it going to take you? 3-4 minutes, not long, right? I give you the phone calls made from Seton Hill University for the past week. Put them in chronological order. They're randomized. How long is it going to take you? Significantly longer. Is there a faster method? I can turn this idea of comparison into an idea of time. When you sort something, how do you do it? If I asked you to put the exams in alphabetical order, you'd pick up an exam, riffle through the ones you'd already sorted to where you think it goes and shove it in, right? That's called an insertion sort. There's an algorithm for that, all you computer science people. There's another way to do it called a bubble sort, where you just pick up the stack, look at the first two. Are they in the right order? If they are, leave them, compare to the second and the third. If not, switch them and keep comparing. Those algorithms take however many things you've got, factorial. Because I've got to keep going through the list every time, right? With a little bit of tweaking, I can reduce that algorithm. So instead of being a factorial algorithm, it is now a roughly squared list. There are 33 of you. What's 33 squared? You've got a calculator. Say again? 1,100. I'll round off. It should take roughly 550 steps to alphabetize the list of exams from random following either of those insertion methods. But if I write another algorithm that's faster, how would I know it's faster? I compare the number of steps for a list of size X for method 1 versus method 2. And you can tell me which one's faster, can't you? By the rate of growth in terms of the number of things in the list. That is called time complexity. It is a measure of how efficient a job is. If I want my web search to work faster, I need to write a more efficient algorithm to search. And that means going through that alphabetical list and finding your exam faster. Right now, there are several methods that are faster than either of the searches I've described. We'll talk about them more next semester in discrete math. There is no reason I can't generalize this idea and do L'Hopital's rule as many times as is necessary to resolve and to determine my limit. Sometimes it takes 3 or 4 or more times, especially if I'm dealing with stuff like trig. Trig functions take quite a while to resolve. Exponentials take a while to resolve. But I can keep doing this as long as I have an infinity over infinity or a 0 over 0. By the way, the signs don't matter. Positive infinity or negative infinity doesn't matter. I'm sorry?
Same.
No. I can do infinity over negative infinity. I can do positive infinity over positive infinity, negative infinity over negative infinity, or that's still indeterminate. However, there are other indeterminate forms. I'm multiplying here. Crap. Now I am approaching 0. This time I'm doing it one-sided. I'm doing it one-sided because of ln of x. ln of x is only defined for positive numbers. So I can't think about what's going on when x is negative. As x gets closer and closer to 0, what happens to x? It's getting closer to 0, right? So this multiplication should be 0 times. Well, 0 times anything is 0, right? What's happening to ln of x as we get closer and closer to 0 from the right? What's that graph look like? I'm looking at each part separately down here. What's happening to my ln of x? Graph ln of x look like as we go this way? That's got a vertical asymptote, which means it's going down to minus infinity. Wait a minute, that means I have 0 times negative infinity. The unstoppable force meets the immovable object. 0 times anything should be 0. Infinity should overpower everything. What do I do with this? This is not determinable the way it's written. I don't know what I can do from here if I leave it as multiplying. But 0 and infinity are kind of related to each other. That was how we got the 1 over x idea in the first place, right? As x goes to 0, 1 over x goes to infinity. Wait a minute, if 1 over x is going to infinity, what if I take this thing and rewrite our multiplication as division? You know, when you're dividing by a fraction, you take the fraction out of the bottom and flip it over, which means I could take something that's on the top, put it in the bottom if I flip it over. So I can change this to be ln of x over what? Say it louder. 1 over x. Now the top of this fraction is going to minus infinity. I could. I feel like writing fraction. Your call. I'm happier with this because the top of this is going to minus infinity. What's the bottom doing? What is the limit as x goes to 0 of 1 over x? It's infinity. And it's positive infinity. So what I have right here is still an indeterminate form, but now it's a L'Hopital indeterminate form.
What's the simple 0?
Isn't that the graph of 1 over x? I'm taking a limit. I'm looking at what happens as we go to 0, and that's going to infinity. And if this is a version that fits L'Hopital's rule, then I can use L'Hopital's rule. And that means that this limit is really this limit. And by L'Hopital's rule, I can resolve this. What is the derivative of ln of x? And the derivative of 1 over x? Well, if I write it as x to the minus 1, it's negative x to the negative 2, which is negative 1 over x squared. Take the fraction out of the bottom and flip it over. And I get x squared over x with a negative sign. But that resolves, doesn't it? That's just the limit of x. Well, minus x, which is 0. So if I run into something where I have an indeterminate product that I'm multiplying, I'm going to use the rules of algebra to make it into division. Then I can apply L'Hopital's rule. L'Hopital's rule only works on indeterminates of the form 0 over 0 or infinity over infinity. And I figured out which one wins, the 0 or the infinity. In this case, the 0 wins. Is it always going to win? Nope. The same thing can be done with subtraction. Again, I would point out to you, there is an asymptote in secant at pi over 2. There is an asymptote at tangent, pi over 2. And they're both going up to infinity when we approach that asymptote from the left. Tangent of x and secant of x. They both go off to infinity. This is infinity minus infinity, which is, again, an absolutely whiskey tango foxtrot moment. Here's the problem. Infinity minus infinity could be anything. You want to make it 1, take x and x plus 1. Aren't they always going to be exactly 1 unit apart, no matter how far off to infinity we go? Want to make it 2, 7, 1/5. I don't care. You could make this number anything you want. So what does it work out to be this time if I want to resolve infinity over infinity? What do you mean? How do I resolve this crap? I need to turn it into division. Only thing L'Hopital's rule works on is division. How can I turn this into division? They're both already fractions. So let's just rewrite them. And then if I combine that to be one fraction, then I have a division problem. And now I can say, is this an indeterminate form? Maybe. If you plug in pi over 2, what's cosine of pi over 2? And sine of pi over 2 is? So that's 1 minus 1 over 0. That's 0 over 0. Bet I'm trippy about that. Which means I know what to do. I do L'Hopital's rule. The derivative of 1 minus sine x. The derivative of cosine of x. If I can do some sort of algebra trick to turn my expression into something that involves division. I'm done. I know how to do L'Hopital's rule then. One of the things we mathematicians are very fond of doing is saying, I don't know how to do this problem, but if I mess with it, it looks like this problem I do know how to do, so let's do that version instead. If I turn something into a case I've already seen, I'm good. However, some cases require a lot more messing with. What is 0 raised to any power? What is a number that isn't 0 raised to the 0th power? So what's 0 to the 0? Is it 0 or is it 1? I can't determine that. That's another indeterminate form. What if I had something that was infinity and ended up being raised to the 0? Well, something to the 0 should be 1, but infinity raised to any power should be infinity. Or what if I had 1? What's 1 raised to any power? 1. Are you sure about that? What if that power is infinite? Mother. How do I get stuff out of powers? Logarithms. Like logarithmic derivatives. If I take the logarithm, then I'll end up with infinity times the ln of 1. What's ln of 1? That's infinity times 0. I turned it into an indeterminate product, which is a case I know how to do. I've reduced it from a case that I have no freaking idea what to do into a case I do know how to do. Rather than me run through this entire thing right here, page 315, example 9. By the way, do you remember the Bank of Sassmore with the compound interest thing? That formula comes from doing an indeterminate power. I didn't make it up. I want to put all of this together. The stuff we did about derivatives. Yesterday, figuring out what the graph looks like. This stuff will allow me to figure out what the ends of the graph look like. How do I know when I have the right picture on here? That's what we're going to do on Monday. If you came in late, please come get your exam. That's how I'm taking attendance today. Enjoy your weekend.